In this next short video, we're going to look at the pointwise or local mutual information and give some further interpretations of mutual information based on that. So, as you may have noticed, when we started talking about entropies, we often started from this pointwise perspective. We started with the Shannon information content before looking at the Shannon entropy as the average of that. With the mutual information, however, I've started with the average quantities, and I'm only going to come to the pointwise quantities now. There's a reason for doing that. Well, there are a couple of reasons for doing that. One reason is that the average quantities here are what people most often talk about, and that's also because in some sense they're a little bit easier to understand and get started with the interpretation for most people. On the other hand, I really like the interpretation of the pointwise perspective on mutual information, so that's what we're going to look at now. So from the pointwise perspective, all of our equations for mutual information between x and y stay the same. We're just changing from looking at variables to looking at realizations of those variables. All of the sums and differences of Shannon information contents are the same as the sums and differences of Shannon entropies. And of course, the average mutual information is still an average over the pointwise values. I mentioned that the pointwise mutual information is sometimes people find it hard to interpret. That's because it can take both positive and negative values. This is very different to Shannon information content, which we saw could only be non-negative, 0 or positive. Let's look at the meaning of positive and negative values of pointwise mutual information terms here. For that, we're going to focus on this equation here, where we look at the pointwise mutual information as a log ratio between a posterior probability on x given knowledge of y and a prior probability on x without any knowledge of y. So here we get a positive value for the pointwise mutual information when our posterior probability of the value of x that did occur given the knowledge of y was larger than the prior probability of x. So what happened here is that knowing the value of y increased our expectation that this realization of x would occur. It increased our expectation, increased the likelihood against the prior probability. That positively informed us about the realization x that happened. Okay, so that's why we get a positive value for mutual information here. We could have the opposite case though, where the knowledge of y may actually reduce our expectation of the realization of x that occurred in comparison to the prior probability not taking y into account. Okay, so if that happens, if the posterior is reduced compared to the prior for the situation that does occur, the knowledge of y has actually misinformed us in this case about x. An example here is if we look at the information we get from a weather forecast about whether it's going to rain or not, for example. So the forecast could say that we're going to get sunshine, but it may actually rain. Now, if we give some credit to our weather forecasters and assume that the forecast is generally giving us some information here, then what we can assume is that the probability of getting rain after a sunny forecast is lower than the probability of getting rain otherwise. So if we plug these sample numbers in, we're going to get a ratio of those probabilities that's less than 1, and therefore a log value for the pointwise mutual information that's negative. So here we were misinformed by the weather report about whether it would actually rain. Importantly, while we can have misinformation for any given realization, on average over all samples in our ensemble, y must provide non-negative information about x, as we already know. Okay, another way that we can look at the mutual information at this pointwise scale is to think about how information comes from exclusions. What I mean by that is exclusions in the probability space. So we can think about a probability mass space here between our two variables, x and y. What we've done is we've written out all the combinations of x and y that we may have in our space here. We've written them out in a way such that this probability mass represents the mass associated with getting x1 and y1 as our realizations. This is the mass associated with the event x1, y3, and so on, such that all of those masses sum to 1. Now, let's think about what information we get from a realization y about a realization x. Let's consider a situation where we have realization y1, and let's say it's realization x1 that occurs in this situation as well. What happens when we read off our realization y1? Well, basically that tells us that other realizations of y cannot occur here. So we can look at the other realizations of y, y3 and y2 in this example, and we can exclude them from the probability mass space, which we've done with the hashing here. So learning that value leads to these exclusions in the joint space. Okay, the potential value of those exclusions is the Shannon information content of y1 here. Okay, the less probable that y1 is, the more we exclude, and the more valuable those exclusions are for informing us, the more potential value there is in those exclusions for informing us about x. Once we've made those exclusions, we then renormalize the probability space to get p of x given y1, and that's what we've got here. We've renormalized our space for the remaining probability values, and we've got 1/3 and 2/3 there. So to evaluate the mutual information, the pointwise mutual information, then in this case, we simply compare our posterior probability of the value x that occurred, which is p of x1 given y1 here, compared to the prior probability on p of x1 over here. We simply compare those two and take the log ratio, and that gives us the pointwise mutual information for this realization. As an exercise, you could consider how exclusions in Guess Who are providing information in this way. Okay, when you play Guess Who and you ask a question, you get a yes or no answer, you're actually excluding part of the probability space when you lay the faces down there. I hope that makes sense. I'm going to skip over the other exercises now. You can follow the activities on our learning site to do those. And what I want to do is give a short conclusion about mutual information. It's a great model-free tool. It's a really nice way to think about it. It's a wonderful model-free tool that we can use to detect relationships between variables, to reveal patterns, and to show how such relationships and patterns fluctuate in time. There are many things that we can do with the mutual information, which we'll see in some of our examples and later in the course. We could use it for feature selection in machine learning. We could use it for space-time characterization of information processing in complex systems, for example in cellular automata here, and this is an example we'll look at later in the course. We could use it for inferring relationships, that is networks in multivariate time series data, such as brain imaging data, which is the image we have on the left here, or between robotic soccer players, which is what we've got on the right. Again, this is something we'll look at further in our course later on.